Hello. In this video, we are going to discuss the mono and dihydrohalogenation of alkynes. Recall that an alkyne has the general formula R1, and then we have a carbon-carbon triple bond, and R2, where R1 and R2 can be different or the same. They can be hydrogens or they can be alkyl groups. The hydrogen halides, which we'll write generically as HX here, that are involved are the strong acids, hydrochloric acid, hydrobromic, and hydriodic acid. In this video, we are going to be particularly concentrated on HCl and HBr. We recall, as mentioned in a previous video, that in the carbon-carbon triple bond, where carbon is sp hybridized, this triple bond is actually three distinct bonds. The first bond is a sigma bond between two s orbitals on each of the carbons. The second and the third bonds are pi bonds, which involve two p orbitals on the carbons. Now, in an alkene, where we have one pi bond, recall that we have electron density above and below the plane, and since there's a buildup of electron density, those are the spots where an electrophile will want to react. Since we have two pi bonds here, we imagine that there is even greater electron density around the carbon-carbon triple bond than around a double bond. And we might naively assume that this increase in electron density around the carbon-carbon triple bond would make it even more subject to electrophilic attack than a carbon-carbon double bond. It turns out that that feature is true, but there's also a competing factor which tends to inhibit the electrophilic attack at the carbon-carbon triple bond. We recall that the simplest and most important of the alkynes is acetylene, which also goes by the IUPAC name of ethyne. So let's look at the reaction between acetylene and hydrogen chloride. We notice that we have a heterolytic bond cleavage of the hydrogen chlorine bond, and the electrons going with chlorine to form chloride. We have electrophilic attack, so the electrons go from the buildup of electric charge to where it's electron deficient, and we know that H plus has no electrons at all, so it is electron deficient. H plus is our electrophile. Let's see what the structure that we get over here is. So, we saw that when we added H plus to a carbon-carbon double bond, which is sp2 hybridized, it reduced the bond order down to a carbon-carbon single bond, sp3 hybridized. Here we have an analogous situation where the carbon-carbon triple bond is reduced to a carbon-carbon double bond. We go from sp to sp2 hybridization. So let's put the resulting part of the acetylene molecule, and then the hydrogen will add to either of the two carbon atoms, which are identical by symmetry. So let's put it on this particular carbon. The carbon that doesn't receive the H plus is the one that's going to bear the positive charge. And we notice that what we have formed here is a vinylic carbocation. And recall that vinylic carbocations are particularly unreactive. They're particularly unstable. So while we do have an increase in the electron density around the carbon-carbon triple bond in an alkyne, that tends to increase the electrophilic tendencies of attack at that position. The resulting carbocation is not particularly stable. So the result of these two competing factors is that we do undergo electrophilic attack at the carbon-carbon triple bond of an alkyne, but it's slightly less reactive overall than at a carbon-carbon double bond. So therefore, the hydrohalogenation of an alkyne proceeds more slowly than the hydrohalogenation of an alkene. So let's kind of finish up the reaction here. So we have a negative charge on chloride. Put it on this side. And again, we have recombination of the carbocation with the anion. So we know that the electrons flow from sources to sinks. So we get a recombination here, and the overall product will have the structure. And the resulting product is chloroethylene. We've drawn the reaction specifically to show it as being anti-addition. It isn't always anti-addition, but overwhelmingly tends to be. So in this particular video, we are always going to show the hydrohalogenation proceeding by anti-addition. Please see the following figures, which show the computed structures of the product, the intermediate, and the reactants. Also, immediately following that figure, see a table, which will also appear later in the video, showing a comparison of the energies of activation for protonation of an alkyne, of various different alkynes, compared to alkenes. And that will show you that alkynes are slightly less reactive because they have greater energies of activation than the corresponding alkene. Once we have formed chloroethylene as our product, an interesting question remains. We know that we can hydrohalogenate an alkene. What happens if we have sufficient hydrogen halide and sufficiently rigorous conditions that we can hydrohalogenate the intermediate product here? So what would happen? Well, we recall, as in the hydrohalogenation of the alkenes seen in a previous video, that we have heterolytic bond cleavage of the hydrogen halide. So we get chloride plus H+. We have flow of electrons from the electron-rich carbon-carbon double bond attacking the electron-deficient hydrogen, which is our electrophile. So now we add hydrogen to the chloroethylene to form a carbocation. We're going to reduce the carbon-carbon double bond to a carbon-carbon single bond. We are going from sp2 to sp3 hybridization. But now this molecule is not symmetric. The two carbons are different. One carbon has a chlorine atom and the other one doesn't. So, to which carbon will the hydrogen atom add? As always, when we have addition of hydrogen, we're going to form the most stable carbocation. But we can apply, to make it easier, the version of Markovnikov's rule that the rich get richer. So we notice that this carbon atom has only one hydrogen, whereas this carbon has two. So we'd imagine that this particular hydrogen will add to the rightmost carbon. So let's see what we get when we do that. So here we've just redrawn our product, reducing the carbon-carbon double bond to a carbon-carbon single bond. Now we will actually add the elements of hydrogen chloride. The hydrogen goes to the rightmost carbon because it already has two hydrogens. Color code this accurately here. It should be green. So going from two hydrogens to three hydrogens. So the chlorine, this will have a positive charge, which we'll show for a second. Whichever carbon does not get the hydrogen is the one that ends up bearing the positive charge. So now the chloride will add to here, chloride, and then we get recombination of the two ions at this particular location, and our overall product will have the following structure. So our product ends up with both of the chlorine atoms attached to the same carbon. This will be a repeating theme when we hydrohalogenate a halogenated alkene, effectively when we dihydrohalogenate an alkyne. So our resulting product is 1,1-dichloroethane. Please see the following figures which show the structures of the reactants, the intermediates, and the products for the hydrochloration or hydrobromination of both chloroethylene and bromoethylene. In each case, we're adding hydrogen chloride to the chloro compound and the hydrogen bromide to the bromine compound. So to emulate the situation that we start with the alkyne and we add a large excess of the hydrogen halide, and the reaction proceeds from alkyne to alkene to the haloalkane. The next alkyne that we're going to look at is the 3-carbon compound. Here where R1 is equal to a methyl group and R2 is equal to hydrogen, and this is called propyne. So now let's look at the reaction of propyne with hydrogen bromide. So the first step, as we expect, is the heterolytic bond cleavage of the hydrogen-bromine bond. The electrons go with bromine, so this has a negative charge. Hydrogen has a positive charge. So now it is electron deficient and an excellent electrophile. We have the carbon-carbon triple bond, which is electron rich. So the electrons flow from the triple bond to the electrophilic hydrogen. In the process, we reduce the carbon-carbon triple bond to a carbon-carbon double bond. So let's see what happens when we do that. And again, we're going to imagine that we have trans addition here, and anti-addition, so we end up getting the trans compound. So now, an interesting question also is, when the electrophile adds H+, these two carbons are not identical. One has a hydrogen and the other has a methyl group. So we can apply the version of Markovnikov's rule that the rich get richer. So we imagine that the hydrogen is going to add to the carbon that already has a hydrogen, and the other carbon will now bear a positive charge. And we have bromide. So in the final step, electrons flow from bromide to the vinylic carbocation that we have here to recombine, and now the final product we end up getting looks as follows. So the compound we end up getting here is 2-bromopropyne. Another way to think about the addition of the electrophile and of the conjugate base is a formulation that Markovnikov himself used, in the sense that he said that the negatively charged group was going to go to the carbon most under the influence of other carbons, which is maybe not the easiest way to apply the rule, but we can see that that is what we have here, because this particular carbon is under the influence. It is bound to a carbon here, whereas this carbon is not attached to any other carbon. So this carbon of the two, of the resulting alkene, is more under the influence of other carbons. So as a result, we get this particular product. So now let's continue reaction of our product with another mole of HBr. And we already know that the first step is going to be the heterolytic bond cleavage to form bromide and H+, which is going to be our true electrophile. That we have flow of electrons from the electron-rich double bond to the hydrogen. So now we need to figure out to which of the two carbons the electrophile is going to bond. Again, we see that this carbon is attached to 0 hydrogens, whereas this carbon is attached to 2 hydrogens. Since the rich get richer, we have to add the hydrogen to the carbon that has the most hydrogens. Also, if you color code it, you notice that, as we did before, the hydrogen has the color, which is the hydrogen that comes from the hydrogen halide, will go to the same carbon that the previous H+ went to. So if you color code it, it's not that difficult to keep track of which species goes where. Again, as we add the electrophile, the carbon-carbon double bond becomes a carbon-carbon single bond. We go from sp2 to sp3 hybridization. So then we add the hydrogen here, and recall that always the positive charge ends up on the carbon that we didn't add the hydrogen to. So this is our intermediate carbocation, and we see it's a secondary carbocation. And then in the final step, we have recombination of the carbocation with the kind of nucleophilic bromide here. So that adds together, and we get our final product. So we notice again that both of the halogens end up attached to exactly the same carbon. So here we have 2,2-dibromopropane as our product of dihydrohalogenation of propyne. The next alkyne that we're going to look at for the reaction is the 4-carbon alkyne, where we have the carbon-carbon triple bond between carbons 1 and 2. So this is the compound 1-butyne. So let's look at the hydrochlorination and then the dihydrochlorination of 1-butyne. So we know we get heterolytic bond cleavage of the hydrogen halide. We get electron flow from the triple bond to the H+. So let's see what we get as far as our intermediate. We know that the triple bond becomes a double bond. We know that in general we're going to have anti-addition, which ends up giving us a sort of trans structure. And again, we have the question, to which of the 2 carbons should we add the hydrogen? We see that this carbon to the right has 1 hydrogen. The carbon to the left has no hydrogens directly attached to it. So 1 is bigger than 0. So the rich get richer. The rightmost carbon gets the hydrogen atom. The leftmost carbon gets the positive charge. So we notice here that we have a vinylic carbocation, and we have chloride, and in the second step, very quick step here, we have recombination of the positively charged carbocation with the negatively charged anion. So electrons flow from electron sources to electron sinks, so where it's plentiful to where it's not. So we get the anti-addition here, and our product is going to be and here we have an ethyl group. Let's realize that's an ethyl group. And our product, after the first addition, of course that's HCl. Let's be chloride. So we have 2-chloro-1-butene as our product. So now let's react with another mole of hydrogen chloride and see what we get in the process. Heterolytic bond cleavage. So now we have to figure out where this hydrogen is going to add. You could add to this carbon or to that carbon. It has to be one of the carbons of the carbon-carbon double bond. We notice that the rightmost carbon has 2 hydrogens, whereas the carbon to the left has 0 hydrogens directly attached to it. So we're only interested in how many hydrogens are directly attached to the carbon. So we see that this hydrogen has to add to the rightmost carbon. So let's see what the intermediate structure is. We know that the carbon-carbon double bond has to be reduced down to a single bond from sp2 to sp3 hybridization. So we're just putting in this structure. So now we need to add the hydrogen. It's going to go to this carbon. And the other carbon gets the positive charge. So you see again that we have formation of a secondary carbocation here. And then in the final step, we get recombination of the positive and negative charges. We have electron flow from the chloride to the carbon that has the positive charge, and our resulting product will look like this. And our product is going to be 2,2-dichlorobutane. So we number the carbons from the right so that the chlorines are at the carbon with the smallest number. So this is 2,2-dichlorobutane as the product. Please see the following structures of the reactions of 1-butyne with either HCl or HBr, either 1 or 2 moles of each. The last of the alkynes we're going to look at in this video is the other 4-carbon alkyne, 2-butyne. So we want to look at the reaction of 2-butyne with first 1 and then a second mole of HBr. So we know that we have heterolytic bond cleavage, which is not a surprise because it forms H+, and we know that HBr in aqueous solution is a strong acid, just like HCl and HI. I have not previously mentioned it, but in this video, as in previous videos, we're assuming that HBr is not reacting in the presence of peroxides. If it does in the presence of peroxides, we get a different mechanism and different products. So, H is now H+, it's electrophilic. We have electron-rich carbon-carbon triple bond. Electrons are going to flow from there to H+. And now we don't have the usual difficulty because each of these 2 carbons is identical by symmetry. So we get identical structures no matter which of the carbons hydrogen is going to add. So that step is nice and easy. Our carbon-carbon triple bond becomes a carbon-carbon double bond. We're assuming we're going to get anti-addition. So we get a trans structure here. And just to keep continuity this way we've been drawing things before, we'll put the hydrogen to the right and then the bromine to the left, but you just as well switch these, it would make no difference as far as the actual product. No, not put that there. So first, just jumping ahead here. So the first step is when we add the hydrogen, that this is the formation of the vinylic carbocation. And then combine two steps and leave something out. So then we have recombination here. And then we're going to get what I had drawn originally, which is so we end up with a trans 2-bromo-2-butene after the addition of the first mole of HBr. Let's now add that second mole of HBr to get the dihydrohalogenation product. Heterolytic bond cleavage. Carbon-carbon double bond is electron rich. So we have flow of electrons from there to the electrophile hydrogen. And now we have a question because the two carbons are not identical anymore. This carbon is attached to a methyl and a hydrogen, whereas this carbon is attached to a methyl and a bromine atom. So the two carbons are distinct. We can apply our version of the Markovnikov's rule that the rich get richer. So this carbon already has one hydrogen, so it's going to get a second hydrogen. Also, we know by reaction that the carbon-carbon double bond will now become a carbon-carbon single bond. So let's put that part in there. So now we add the hydrogen, it has to go to this particular carbon. And we know that whenever we add the hydrogen to one carbon, the positive charge will end up on the other carbon. The heterolytic bond cleavage of HBr led to bromide here. And then in the final step, we have flow of electrons from bromide to the positively charged carbon. So let's see what we get for our final product here. So we end up with a 2,2-dibromobutane. We see something very, very interesting here. That whether we start with 1-butyne or 2-butyne, and we do a monohydrohalogenation, we get different products for 1-butyne and 2-butyne. But if we react either 1-butyne or 2-butyne with 2 moles of the hydrogen halide, we end up with exactly the same product. We end up with either the 2,2-dibromobutane or the 2,2-dichlorobutane. Please now see the structures for the reactions of 2-butyne with HCl and or HBr, and then also see tables showing the computed energies of the reactions for either mono or dihydrohalogenation of the alkynes. I thank you very much for your kind attention. Have a good one.